Welcome back to Module 1. In our previous lecture, we established the macroscopic physics of the solar resource. We tracked an incoming flux of photons from the sun, through the Earth's atmosphere, and into our semiconductor thin film, mapping how that light is absorbed exponentially, according to the Beer-Lambert law. But what actually happens at the exact moment of absorption? To answer that, we must leave classical optics behind, and enter the realm of quantum mechanics and solid-state physics. Today we are going to explore semiconductor band theory. We need to understand the internal electronic architecture of our materials to see exactly where our electrons reside, how much energy they need to break free, and why some materials make fantastic solar cells while others are completely useless. Let us start with a single, isolated atom. Quantum mechanics dictates that an electron orbiting this nucleus can only occupy specific, discrete energy levels. It cannot exist in the empty space between these levels. However, a functional solar cell is not made of isolated atoms. It is a macroscopic crystal lattice containing roughly 10 to the power of 22 atoms per cc. As we bring these atoms close together to form a solid crystal, their outermost electron orbitals begin to overlap. Here, the Pauli exclusion principle takes over. This fundamental principle states that no two electrons in an interacting system can share the exact same quantum state. Because billions of atoms are interacting, those originally sharp, discrete energy levels must split into billions of distinct, infinitesimally spaced sublevels to accommodate all the electrons. Macroscopically, these levels are packed so tightly together that we treat them as continuous, quote, bands of allowed energy. The two most important bands for optoelectronics are the valence band and the conduction band. The valence band contains the highest energy electrons that are still bound to specific atoms at absolute zero temperature. The conduction band is the next highest energy band. It is largely empty at absolute zero, but if an electron is promoted here, it is free to move through the crystal lattice and contribute to an electrical current. The defining characteristic of any solid material is the gap between the top of the valence band and the bottom of the conduction band. This region is a forbidden energy zone, where no electron states can exist. We call this the band gap. The size of the band gap determines whether a material is an insulator, a conductor, or a semiconductor. In insulators, the band gap is massive, often greater than 4 or 5 electron volts. Visible photons simply do not have enough energy to kick an electron across this void, which is why materials like glass are transparent. In conductors, like metals, the valence and conduction bands actually overlap. Electrons flow freely, but they cannot store the potential energy of an incoming photon to create a voltage. Semiconductors sit perfectly in the middle. They have a moderate band gap, typically between 1 and 3 electron volts. This is the Goldilocks zone for photovoltaics. When an incident photon from our solar spectrum strikes the crystal, and its energy is greater than or equal to the band gap, the photon is absorbed. Its energy excites an electron from the valence band into the conduction band, leaving behind a positively charged void called a hole. This creation of an electron-hole pair is the fundamental origin of all photovoltaic power. Up to this point, we have treated energy bands as flat, horizontal lines. But in reality, an electron's energy depends heavily on its crystal momentum, which is represented by a wave vector. When we plot energy against this wave vector, we get a dispersion diagram, often called an EK diagram. Calculating these exact dispersion relations from first principles is precisely what computational materials scientists do when running density functional theory simulations, using advanced codes like quantum espresso. By computationally mapping these band structures, we can accurately predict the optoelectronic behavior of new, unfabricated perovskite compositions before we even enter the lab. These diagrams reveal a crucial distinction: direct versus indirect bandgaps. In a direct bandgap semiconductor, the maximum energy of the valence band aligns perfectly with the minimum energy of the conduction band at the exact same momentum state. An electron can absorb a photon and jump straight up. In an indirect bandgap material, like traditional silicon, the maximum and minimum are misaligned. A photon carries plenty of energy, but virtually zero momentum. Therefore, for an electron to make the jump, it must simultaneously absorb a photon and interact with a phonon, which is a quantum of lattice vibration, to shift its momentum horizontally. This three-particle interaction of an electron, a photon, and a phonon is statistically unlikely. This is why indirect materials like silicon require films that are hundreds of micrometers thick to absorb enough light. Conversely, most metal halide perovskites are direct bandgap materials. This allows for massive optical absorption in ultra-thin films, drastically reducing material costs. We know the energy bands exist, but where exactly are the electrons sitting within them at a given temperature? To figure this out, we need two mathematical functions. First, the density of states. Think of this as the number of available seats in our energy band theater. Just because a band exists doesn't mean there is equal room everywhere. The number of states typically increases proportionally to the square root of the energy as you move deeper into the band. Second, we need to know the probability that a given seat is actually occupied by an electron. Electrons are fermions, meaning they obey Fermi-Dirac statistics. The probability function states that the chance of finding an electron at a specific energy level equals 1, divided by the quantity of 1 plus E, raised to the power of the energy minus the Fermi level, all divided by Boltzmann's constant times the absolute temperature. The Fermi level is a vital thermodynamic concept. It represents the specific energy level, where the probability of finding an electron is exactly 50%. By mathematically multiplying the density of states by the Fermi-Dirac probability and integrating across the energy band, we can calculate the exact concentration of free electrons in the conduction band. The result tells us that the electron concentration equals the effective density of states in the conduction band, multiplied by an exponential decay function dependent on how far the conduction band is from the Fermi level. Let's summarize. Atoms bonding in a crystal lattice cause discrete atomic energy levels to broaden into continuous valence and conduction bands. The forbidden energy gap between them dictates what wavelengths of light a material can absorb. Furthermore, computationally mapping energy versus momentum tells us whether the material is a direct or indirect absorber, while Fermi-Dirac statistics allow us to track the carrier populations. However, an intrinsic semiconductor with its Fermi level perfectly in the middle of the bandgap cannot generate an electrical current on its own. It lacks the internal asymmetry required to separate the photo-generated electron from the hole. In our next lecture, we will solve this by introducing impurities into the lattice, a process called doping, and we will finally build the engine of our solar cell, the p-n junction.